If you drive a truck with oversized tires, how will your speedometer be affected? Explain your answer. Well, the speedometer actually counts the number of rotations, and it knows how far each rotation is, and it does a little bit of math and figures out your velocity. So if your rotation itself has a larger circumference, it's going to change what that velocity is. So with an increasing radius, because you're getting oversized tires, they're going to be larger, they're going to have a larger radius. Each rotation will have an increased circumference that it's rotating through. So a smaller tire, when it rotates one time, will go a set distance. A larger tire, when it rotates one time, it's going to go even further. So for each rotation, you're going to have a longer distance traveled in that same amount of time. Your car essentially, or your truck, will go farther in that set amount of time and will essentially be going faster than what the speedometer indicates. After fixing a flat tire on a bicycle, you give the wheel a spin. If it rotates 3 times, through what angular displacement did the wheel rotate? Our given information is that you're rotating 3 times. So it'll be 3 times whatever rotation gives you, and we know that the rotation is going to be based on 2 pi radians. So 3 times 2 pi, which would be 18.85 radians. What is the angular velocity of the second hand on a clock? What's the angular velocity of the minute hand on a clock? With angular velocity, we're looking at omega. The units for angular velocity is radians per second, so if we could set this up to where our solution has radians per second, we're in good shape. How many radians when the second hand goes all the way around? Well, it's 2 pi radians. It goes all the way around. And how long does that take? 60 seconds. So we take our 2 pi and divide by 60, leaving the radians and the seconds alone because those are the units that we desire. 2 pi divided by 60 would give us 0.105 radians per second. Now we're going to do the same thing for the minute hand. Again, omega being angular velocity, units are radians per second. We want to set up our information so that we're provided the desired units, radians per second. It's 2 pi radians for the minute hand to go all the way around. It takes 3,600 seconds for that to happen. 60 seconds times, well, it's 60 minutes. Oh, 3,600, is that right? Yeah, that's totally right. All right, so 3,600 seconds is an hour, and that's how long it takes for it to go all the way around. It gives us 0.00174, or 175. And if we want to clean that up, that'd be 1.75 times 10 to the negative third radians per second. An old phonograph record with 0.2 meter radius revolves at 45 revolutions per minute. First, we're going to solve for the angular velocity. Angular velocity is omega. And if they've given us 45 revolutions per minute, let's set that up with 45 revolutions over 1 minute. We want radians per second, so we're going to have to convert the revolutions. 1 revolution is 2 pi radians. And 1 minute is 60 seconds. We can set this up with a track if you're comfortable that way, or we can just do a series of fractions by multiplying by new fractions. As long as the top is equal to the bottom, we're just simply multiplying by 1 and changing the units along the way. 45 revolutions per 1 minute. We know that 2 pi radians is the same as 1 revolution. If we put revolution on the bottom on the next fraction, they'll cancel out because revolution is on the top on the previous fraction. That gets us into radians, but we still have those pesky minutes, so we need to put 1 minute on top, 60 seconds on the bottom, so that now minutes cancel out. We're left with radians per second as our final units. So let's cancel out those units. 45 times 2 pi times 60 should get us about 4.71 radians per second. What is the translational velocity? Let's remember translational velocity is the linear velocity, the one that we're a lot more familiar with, that we've worked with all year long. We know that translational velocity will be the angular velocity times the radius, or 4.71 times 0.2, 4.71 being the solution from the previous answer, or the previous question, times the 0.2 that they gave us in the problem being the radius. When we multiply those, we should get something near 0.942 meters per second. And being meters per second because we're replacing the radians with what the radius is, and the radius is in meters. So we multiply in that number and bring in its new unit. Once the motor is turned off, it takes 0.75 seconds, so time is 0.75 seconds, to come to a stop, final velocity being 0. It comes to a stop. What is the average angular acceleration? Well, we know that angular acceleration is the change in angular velocity over time, delta omega over t. Change in omega is final minus initial, so omega minus omega naught over time. We know that the final is 0. 0 minus 4.71 would be negative 4.71 divided by the time, 0.75. So final minus initial, final is 4.71. I'm sorry, the final is 0 minus initial, which was 4.71, will give us the negative 4.71 divided by 0.75. That should give us something around negative 6.28, yep, radians per second square. How many revolutions did it make while coming to a stop? Well, revolutions, we know that revolutions and radians are kind of related. We can go from one to the other because one revolution is 2 pi r. If they're asking for revolutions, if we can solve for radians, we can then convert to revolutions. So we're asked for revolutions. How many revolutions did it make while coming to a stop? We can say that theta, which gets us radians, is equal to omega naught angular velocity, initial angular velocity times time, plus 1/2 angular acceleration times t squared. Theta is equal to omega naught t plus 1/2 alpha t squared. Plug in the numbers we have, 4.71 times 0.75 plus 1/2 of negative 6.28 times 0.75 squared. This is going to get us the number of radians. Again, this is getting us theta. Theta, the unit of theta is radians. We should get about 1.77 radians. Now that we have radians, we can convert to revolutions, what the question's really asking us. 1.77 radians, we know that 2 pi radians is 1 revolution. But since radians is essentially starting at the top, we're going to say it's like over 1. We're going to put 1 revolution over 2 pi radians. That's is equal to 1. They cancel out. Radians will cancel out here. We have 1.77 essentially divided by 2 pi. When you're doing this, don't put 1.77 divided by 2 pi in your calculator unless you put parentheses, 2 pi, close parentheses, or you divide by 2, then divide by pi. If you just put it together, no parentheses, the calculator will think you're dividing by 2 and then multiplying by pi. That's the wrong answer. The correct solution for this would be 0.28 revolutions. Number 5, how many revolutions does a CD make when accelerating from rest? So we know that the initial angular velocity, omega naught, is 0. to 7598 revolutions per minute in 5.44 seconds. So they've given us a time 5.44 seconds, but in order to get the omega that they're giving us, we've got to convert the revolutions per minute. So we're listing out all our knowns. It's so much easier when we have our knowns listed out, our given. Don't forget your guess method. Listed our given, our unknown, equation, substitute, solve, all of that. So we're going to convert this revolutions per minute into radians per second into omega. 7598 revolutions per 1 minute, so 7598 revolutions over 1 minute, times 2 pi radians over 1 revolution, revolutions cancel out, times 1 minute over 60 seconds, and the minutes will cancel out. And that will get us our final angular velocity of 795.26 radians per second. Let's check in a calculator. Again, we're not messing with the radians or the seconds because those are the desired units. The other numbers, if they're on the top, we're multiplying them. If they're on the bottom, we're dividing them. Now that we got it through the calculator, 795.67 is the final angular velocity. Now that we have that, we can put it into a formula based on the information that we have. What are we missing? What do we not have? It looks like we don't have angular acceleration, so let's use a formula that does not have angular acceleration. Theta is equal to 1/2 omega plus omega naught times time. Omega is equal to 1/2, and then we would have essentially 795.67 plus 0, so you don't have to put that in, times the time of 5.44. Once we solve that, we're solving for omega. And again, the reason we want to solve for omega is so that we can get to revolutions, because revolutions kind of run through radians, and what uses radians? Theta. All right, let's get this through our calculator so that we have what theta is. 2,164.22 radians. We haven't answered the question yet. We're just on our path in order to solve this. So now we need to take the 2164.22 radians and we're going to multiply that by 1 revolution over 2 pi radians. The radians will cancel out, and we're going to be left with units of revolution. So 2164.22 divided by 2 pi. Again, don't forget, you're going to divide by open parentheses, 2 pi, close parentheses, or you're going to do it sequentially, divide by 2, enter, divide by pi. It's miserable to have the right methodology, but bad calculator. Our final answer, 344.45 revolutions. Back of the page. A spinning sphere accelerates at a rate of negative 9.1 radians per second square. So that's our alpha. That's our angular acceleration. If the sphere slows to 6 radians per second, so this looks like our final angular velocity, in 2.3 seconds, so our time is going to be 2.3 seconds, how fast was the sphere initially spinning? So ultimately, we're going to be looking for omega naught, our initial angular velocity. This looks like our WOTAD equation. So final angular velocity is equal to initial angular velocity plus alpha times time. If we rearrange this, we would have initial angular velocity is equal to final angular velocity minus alpha times time. I've just basically subtracted AT or alpha t to the other side. Let's plug in our numbers. We would have 6 minus 2.3 times a negative 9.1. So you've got kind of that double negative there. It essentially adds. But in our calculator, we have negative 9.1 times 2.3. And then we just add in that 6 because the negative and the minus. When we do that, what do we get? .9693 radians per second. A chef spins pizza dough with an angular acceleration of 2 radians per second square. So they've given us the acceleration, 2 radians per second square, and it asks us how many radians, otherwise known as what's the theta, has the pizza dough spun through after 10 seconds. So I feel like we don't have all the information. All right, we've been given alpha, we've been given time, we're looking for theta. Well, you need 3 things. In kinematics, you need 3 knowns. So we have to make an assumption, don't we? An educated guess. When the chef grabbed the pizza dough and started spinning it, what was the initial angular velocity, do you think? Probably not spinning when he first picks it up, so probably 0. It's a safe bet. So we're going to say that theta is equal to initial angular velocity times time plus 1/2 angular acceleration times time squared. And yes, it looks like I left the square off of my equation, but I remembered it on the second line. So theta ends up being 10 squared, which is 100 radians. 1/2 times 2 times 10 squared. How many times has the dough spun around in this time period? How many times has it spun around? It's asking how many revolutions. Well, if we got 100 radians, and we know that 2 pi radians is 1 revolution, we just need to divide by 2 pi, and the radians will cancel out. 100 divided by 2 divided by pi, or 100 divided by parentheses 2 pi parentheses, will give us the solution of 15.92 revolutions. That's how many times it spun around during that time period. Just adding those notes on the side. What is the dough's angular velocity after 5 seconds? So we have a new time. We're looking for omega, final velocity, at time of 5 seconds. We do still have our alpha, our angular acceleration, and we know that the initial was still 0. So using our WOTAT equation, final angular velocity equals initial angular velocity plus angular acceleration times time. Omega is equal to omega naught plus alpha t. Omega naught is 0, so 2 times 5 is 10 radians per second. Rank A to C from the lowest angular acceleration to the highest angular acceleration. So we need to know what the alpha is for each and then make the comparison. A car wheel rotating from rest, so we have omega naught, to 35, we have omega, in 28.57 seconds. So we have time. Those are the 3 that we have. I'm going to use the WOTAT equation, and I'm going to plug in what I have, and I'm going to solve for alpha. Starting with the equation, plugging in the numbers, solving for alpha. Looks like I'm getting, for this particular one, 1.23. For the second one, a truck wheel rotates 500 radians, so they've given me theta at 500, from rest, so my initial angular velocity is 0, in 26 seconds, so my time is 26. What do I not have? I don't have final angular velocity, so I'm going to use theta is equal to initial angular velocity, omega naught, times time, t, plus 1/2 angular acceleration, which is alpha, times time squared, t squared. Plug in the information I have, and I get 1.48. The final one, a Jeep wheel rotating at 750 radians, my theta, from rest, so omega naught is 0, to 45 radians per second. That's my final angular velocity. So I've got omega squared is equal to omega naught squared plus 2 alpha times theta. So far my solutions, my first one's 1.23, my second one's 1.48, so it's getting bigger. And then with this one, it looks like I'm going to get 1.35. So my lowest is going to come from A, 1.23, The next lowest is C at 1.35, and my highest is B at 1.48, going from smallest to biggest, A, C, B. It asks us to indicate the equations that support your reasoning and explain how each equation provides support. I'm just going to go ahead and list the equations for you. They're listed, but much too small to really read next to A, B, and C. And how do I explain how they provide me the best support? When I list my given, I have 3 known, and I'm looking for alpha in each. My kinematic equations are set up that if I have 3 known and 1 unknown, I choose the equation that works best for that situation. I've made it to number 9. Number 9 is the final question on the worksheet. Starting from rest, so my omega naught is 0 radians per second, the tub of a washing machine reaches an angular speed of 5.2 radians per second. So my final angular velocity is 5.2 radians per second with an average angular acceleration of 4.0 radians per second squared. So my alpha is 4 radians per second squared. How long does it take the spin cycle to come up to speed? So I'm looking for time. What angular displacement, looks like I'm looking for theta as well, does the tub rotate through as it reaches the angular velocity? So I think I'm going to do time first. I'm going to use the WOTAT equation. I'm just calling it WOTAT because that's the way it looks like it's spelled after the equal sign. Kind of like we talked about VOTAT when we were doing linear. 5.2 is equal to 4t because omega naught is 0. So 5.2 divided by 4 is 1.3 seconds for my time. As I'm doing theta, I could utilize my time, but what if I made a mistake? If I don't have to use time, let's avoid using time. So I'm going to use an equation that doesn't have time. I'm going to say omega squared is equal to omega naught squared plus 2 alpha times theta. Plug in our numbers. We've got 5.2 squared is equal to 0 squared plus 2 times 4 times theta. .2 squared divided by 8 is 3.38 radians.